interaction with the novel cryoprotecting agents. She then carried out her PhD study from 2004 and 2008 at Dublin City University, where her work involved in the preparation of fast field cycling NMR characterization of membrane-bound nanoparticles and nanoparticle assemblies for biomedical applications. So after completing a postdoctoral assignment, so between 2008 and 2009 at the same university, where she worked on the development of an hierarchical assembly of an hybrid magnetic nanoparticle clusters for applications in magnetic resonance imaging. Kalra moved to New Zealand and began her current assignment to Dago in December 2009. Kalra has been an associate investigator in the McDermott Institute since 2010. Her research interests are towards the design, synthesis, and the characterization of functional nanomaterial. The interest in the nanoscale material lies in the fact that their size, shape, and the composition can dramatically affect their physical and chemical properties. This phenomena can be exploited in order to develop a new material with the tunable property for a broad range of applications. So now over to Dr. Kalra. So she's going to deliver a talk on the tuning metal organic framework, nanocrystals using microemulsions. So thank you.
Thank you so much. Am I still sharing my screen or has it disappeared?
You can reshare again, yeah.
Okay, there we go. That's it there. Excellent. 1 moment. There we go. Thank you. And thank you so much. Kia ora. That's greetings from the South Pacific Ocean, the South Pacific down here in Aotearoa or New Zealand. I'd like to start by sincerely thanking the conference organizers. I really appreciate both being invited to speak, but also for organizing what looks like a really fantastic week of talks. Given what's happening in the world, I really appreciate that we can all come together and share our science with one another. So many thanks for that. And wherever you are watching in the world, I wish you well, and you and your loved ones as well. So just a wee bit about New Zealand. So I'm down here, the University of Otago is down here in Dunedin, which is almost at the very bottom of New Zealand. Our campus is tucked away here, right alongside the Otago Harbour and the beautiful Otago Peninsula. So this is just an overview of our campus. I'm sitting in a building just off the photo here. At the moment, just a couple of pictures of our city and our peninsula. This peninsula here, which is known as the wildlife capital of New Zealand, and perhaps you can see why. And I'll get to why I'm showing you these photos in a moment. First, I'd also like to introduce you to the McDermott Institute for Advanced Materials and Nanotechnology. So while it may look like we're quite isolated down here at the bottom of the world, in fact, I'm connected to an amazing group of about 75 other materials scientists based at universities and research institutes around New Zealand through this McDermott Institute for Advanced Materials and Nanotechnology. So we're a virtual institute, we're funded by the New Zealand government as a Centre of Research Excellence, or a core. This model of Centres for Research Excellence was established in 2001 by the New Zealand government, really to encourage the development of excellent tertiary education-based research that's both collaborative and strategically focused. So our focus in particular within the McDermott Institute is to create and explore innovative, sustainable materials to improve the lives of both New Zealanders and hopefully those around the world. And we also partner with industry and government to try and address global challenges. So things like clean water, renewable energy, climate change, things like that. This is a relatively recent photo from our annual symposium. And the reason that I've spent a few minutes telling you about our institute is that I would love to welcome you in person down to New Zealand. So I hope to entice you to consider coming down for the AMN 10 conference. So the McDermott Institute hosts the International Conference on Advanced Materials and Nanotechnology every other year. It was supposed to be held February 2021, so last month. Obviously that couldn't happen, but it has since been rescheduled for the 31st, starting the 31st of January 2022 in Rotorua, New Zealand, which is on the North Island and very well known for its geothermal activity. So please mark your calendars, and I'd love to see you all here. I believe the last AMN conference was well over 500 participants. The largest nanotechnology conferences, if not the largest nanotechnology conference in the Southern Hemisphere. So with that being said, I'll start with just a little bit. It was a very thorough introduction. Thank you very much for that. Just a little bit of a research overview of the type of work that we do in my group. So I think the work that I do can perhaps most accurately be described as we use colloidal-based approaches to develop functional nanoscale materials. So we try to keep active in both fundamental studies and applied research, and use both research streams to try and help inform the other. So on the fundamental side, we're particularly interested in surfactants, micelles and microemulsions, and things like how various secondary surfactants might partition or interact or diffuse within the environment of microemulsions in order to try and understand or better utilize various surfactants as capping agents for nanoparticles that are synthesized within reverse micelles or microemulsion systems. We're particularly interested in interfacial interactions at nanoparticle surfaces, and we do a lot of work, as you'll see today, with respect to nanoparticle synthesis and functionalization within reverse micelle or microemulsion systems. And then on the applied side, we design nanoparticles with various properties for a variety of applications. So I've been well involved with the dental school here at the University of Otago, designing silver nanoparticles, antimicrobial silver nanoparticles, and incorporating them into things like dental filling materials, as well as bone scaffolds. We're interested in magnetic nanoparticles, as well as gadolinium-based metal organic frameworks as MRI contrast agents. We've done some work with some coordination polymer nanocrystals as heterogeneous catalysts, and utilizing nanoparticles as substrates in order to assemble single molecule magnets toward device applications. And finally, what I'll be focusing on today, although I'm not really going to talk much about the application, but the development and design of porous materials, really ultimately with the goal in mind eventually of some gas separation and storage. So what I'm going to talk about today is really certainly not a complete story by any means. In fact, it's quite the opposite. What I'm really presenting is what I hope to be the very, very beginning of a long and hopefully fruitful and productive research program. So just to start, I'm sure as many of you know, I'll give a brief introduction to metal organic frameworks. So they're a class of hybrid materials formed by the self-assembly of polydentate organic bridging ligands and metal ions. They can be formed from a wide selection of metal ions and almost an infinite number of organic bridging ligands. So they can be engineered with really an unprecedented range of compositions and therefore properties. So they have such a high degree of tailorability. So it's led to the synthesis of over 20,000 discrete, unique MOFs to date. And they emerged on the scientific scene in the 1990s, and since then have really proven to be quite a transformational new class of materials. They've captivated scientists around the world because of their fundamental properties, their chemical functionality, their diversity, their porosity, the ability to tune their pore environment, the ability to, the capacity for crystal and defect engineering, and for a variety of other reasons. Beyond that fundamental interest then, they've demonstrated really quite superior properties to conventional materials for a wide variety of applications, things like the separation and storage of small molecules, catalysis, sensing, and biomedicine, just to name a few. And all of those applications aim to exploit the inherent porosity and the very large surface area or high pore volume of these metal organic frameworks. So if MOFs are so fantastic, as I've just described, and I think they are, and many other people think they are, why are we particularly interested then in nano-MOFs? Well, as we've talked about, MOFs on the macroscopic scale, or bulk MOFs, we know they're structurally and chemically diverse. We know they have a high surface area and pore volume, etc. But as most materials do, they have a variety of limitations that are actually limiting their potential for practical application. So for instance, slow or restricted diffusion of guest molecules into the crystal interior can inhibit the use of MOFs for applications that rely on small molecule uptake. Additionally, they're synthesized typically in their as synthesized form. They're solid powders, and that means that they have limited processability. And of course, there's a lot of research going on into more processable forms of MOFs and how to make them into a variety of different types of materials. They can also have poor long-term stability. So as a result, our group and many others around the world are interested in or are turning their attention toward the fabrication of MOFs on the nanoscale. So the fabrication of what I'll abbreviate as nano-MOFs or nMOFs. So it's gained a lot of momentum in recent years. They have quite distinct advantages over bulk MOFs. They have increased specific surface area. They have a decreased diffusion distance. So now the majority of the pores are located at the surface, decreasing that diffusion distance of guest molecules. So that can lead to superior loading potential, some accelerated diffusion kinetics of guest molecules. We've seen many examples of nanoscale MOFs that are dispersible in a variety of solvents. This also increases their processability. They have improved bioavailability. They have a size small enough to be a physical size that enables intracellular delivery, for instance. And hierarchical porosity has been demonstrated, as well as a variety of other properties that differ from those in the bulk scale. So what are the challenges then? So despite the fact that nano-MOFs really can expand the scope of utility of their bulk counterparts, I think I've calculated it to be less than 0.25% of the 20,000 plus unique MOFs that have been prepared at the macroscopic scale have actually been prepared on the nanoscale. So really a tiny, tiny fraction of the known MOFs have ever been prepared on the nanoscale. In particular, nano-MOFs with diameters less than 20 nanometers are particularly rare. There are a variety of factors that have led to this disparity. First of all, the first challenge is that the characterization of nano-MOFs can be quite challenging. So their submicron crystal size is too small in many cases for structure determination by conventional X-ray crystallography techniques. So they're also prone to beam damage using electron microscopes. And then the second challenge, or the second of several challenges, but the second one I'll mention today, is that the nucleation and growth mechanism or mechanisms of nano-MOFs really remains far from being fully understood. And without that, the reliable production of MOF nanocrystals will continue to remain elusive. There are some proposed theories that hold true in many cases, and in fact hold true sometimes in most cases, but there really doesn't seem to be any theory that seems to apply all of the time. So to address these two challenges, with respect to the first challenge and the characterization, we've really been inspired by some of the key developments in electron diffraction techniques that allow the collection of three-dimensional electron diffraction data for crystals in the size range of about 10 to 100 nanometers using transmission electron microscopes. So this has enabled structure determination of both micro and nanocrystals. It's commonly known as microcrystalline electron diffraction, or micro-ED. And it's commonly applied to study zeolites and small molecules and proteins and metal oxide crystals. But to date, it's had very little application for structural determination of MOFs. So we've been exploring the use of micro-ED for a range of nano-MOFs that we've prepared using our microemulsion systems. And we've had some recent success in this area, but that's not actually going to be the focus of my talk today. Instead, I'm going to focus on that second challenge, which we think can be at least partially addressed through the use of a microemulsion-based synthesis. So at the very least, I hope I can show you today that we think microemulsion-based syntheses can provide some new insight into some of the potential growth pathways or growth mechanisms. And these can be revealed through really a systematic approach of finely tuning the synthetic conditions in a way that we can do with a microemulsion-based synthesis that can't easily or necessarily be achieved using more conventional approaches. So perhaps I can say that a little bit more succinctly by saying that the reason we want to use microemulsions to prepare nano-MOFs is that it provides a rapid, a room temperature, and a reproducible synthesis of nano-MOFs, often with well-defined surface chemistry, which I may or may not have the time to talk about today, without the need for post-synthetic modification. We also think we can gain some fundamental understanding of how nano-MOFs form and how they grow, and how the synthetic parameters affect the physicochemical properties, and the potential to access new topologies that have yet to be produced on the macroscopic scale. And I will show an example of this today. So by way of introducing the microemulsion method that we use, over here, we start with, and this is just sort of the basic approach that we use, and it can certainly get more rapidly complicated. But we have, first of all, a single three-phase microemulsion system where we have an oil-based continuous phase, a surfactant that forms the reverse micelles, within which we have some polar phase. And that polar phase then is used to dissolve the reactant. So it might be the ligand, for instance, here, and a separate microemulsion, in which case, or within which we dissolve the metal salt. We then mix those microemulsions together, and the reverse micelles will collide and coalesce and exchange their contents. We allow them to react for a particular time. And then we can induce a phase separation, for instance, by introducing an excess of the polar solvent, which can rupture those reverse micelles, induce that phase separation, and then we can collect the nanocrystals. As you might imagine, there are really a whole wide range of parameters and of synthetic conditions that can be adjusted. Things like the surfactant type, so we can have ionic or non-ionic surfactants forming the reverse micelles. We can certainly control the reverse micelle size, the ligand to metal ratio, so the concentration within these reverse micelles. We can control the pH. We can control the ionic strength. We can control whether we add the ligand microemulsion to the metal microemulsion, or the metal containing microemulsion to the ligand containing microemulsion. The rate of addition of one to the other. And in that way, we can effectively control the concentration of ligand and metal ion throughout the course of the reaction. We can control the number of microemulsion systems used. So we could, after we mix the two microemulsions, we could add in a third microemulsion that contains either an acid or base, for instance, to control the pH or to change the pH, or another microemulsion that contains yet another metal or another ligand, so that we can start forming hierarchical structures or bimetallic MOF structures. And we can change the solvent conditions, et cetera, et cetera, et cetera. So while this is fantastically exciting because we have a very high level of control of all of these different parameters, again, in a way that we don't necessarily have using more conventional approaches for MOF formation, you can see how very rapidly this would require a very high number of experiments or high number of experiments in order to test all of these different parameters, some of which can easily be isolated, and others, some of these parameters are inherently linked. So it does become quite complicated very quickly. But what I want to do today is, with the time I have today, I just want to present a small selection of some of the experiments we've performed where we modify some of these experimental parameters. So in some cases, like this example that I've shown here, this is a gadolinium-based MOF. This is a gadolinium BTC, so that's a benzene tricarboxylic acid. Apologies there. And we've quite simply varied the reaction time. So that means we have mixed microemulsion 1 containing the BTC ligand and microemulsion 2 containing gadolinium chloride. We've mixed them together and allowed them to react for 2 minutes, 4 minutes, 6 minutes, and 8 minutes. And as you might expect, you can see the growth of these, what we can call nanorods, perhaps. But interestingly, these form in 10 minutes at room temperature. And if we follow the X-ray powder diffraction pattern, as you might expect, again, we see an increase in the crystallinity the longer we allow these to react. So there's perhaps nothing very surprising there, and perhaps nothing particularly surprising here. But what I want to do here is show this example because I want to come back to rate of addition in a few slides. So this was the formation of ZIF8. So this is a zeolitic imidazole framework. So we have a zinc metal and a methyl imidazole ligand. And in this case, we adjusted the rate of addition of one microemulsion to the other. And perhaps, maybe, if you were to count enough particles, or if you were to squint your eyes enough, you might be able to suggest perhaps that there is a trend in particle size or morphology or maybe size distribution. I wouldn't be convinced that that's the case. But again, I'm showing this example because while there's nothing too surprising here, rate of addition does, in fact, when combined with a change in solvent conditions, does in fact have quite a striking effect on some of the crystal properties, which I'll show in a moment. So if we stick with the ZIF8 for a moment, one of the other parameters we can adjust would be the order of addition. So whether ligand is added to metal or metal is added to ligand. And here you can start to see that there's a difference in the size and the morphology of the crystals. But even though there's a distinct change in the size and the morphology, in all cases, you can see the X-ray crystal structure here, the X-ray powder diffraction pattern. The bottom here is that calculated for ZIF8, and the rest are all prepared using the microemulsion method, changing a variety of conditions, such as ligand to metal, metal to ligand, and includes the rate of addition. And in all cases, you can see here, all of the structures, all of the resulting nanocrystals are in fact ZIF8. They all match the pattern, all match the simulated pattern there. But we can go a wee bit further then and compare the gas adsorption properties. So what you're looking at here is the N2 adsorption desorption isotherms for a variety of the ZIF8 nanocrystals. In black here, this is the isotherm for ZIF8 that was produced using a conventional solvent thermal synthesis. So this is conventional bulk ZIF8 macroscopic crystals, and these are all the nanocrystals prepared using a variety of synthetic conditions using the microemulsion method. And what you can see here is that in all cases, the nanocrystals prepared using microemulsion-based techniques show hysteresis. And hysteresis is known to be associated with the formation of mesopores. And in fact, I didn't include the image, apologies, but we actually are able to see with SEM the presence of the mesopores in these xiphate crystals. So we're going to explore these a wee bit further, but we can clearly see, regardless of the synthetic conditions, in this case, using the microemulsion method, we can tune or we can change the synthetic conditions, but it doesn't matter how we tune the synthetic conditions, we always get xiphate and we always get the formation of mesopores. And that always differs from bulk xiphate. We then moved on to a different MOF, or a different ligand and metal ion. And I do apologize, I'm sort of being intentionally vague here because this is quite new results that we're still working on and we're quite excited about. But in this case now, we have our ligand, we have our metal ion. And in all cases, when we mix our microemulsion together, regardless of the synthetic conditions, we always initially, after the addition of one to the other, start with the formation of nanospheres. And it's probably a little bit hard to see on the screen there, but we do have nanocrystals around 30, probably 20 to 30 nanometers. After that, then, these nanospheres seem to develop into either needles, hexagons, or what we call noodles. In fact, I can show the pictures there. Simply with a difference in one case, if we use a solvent A, we'll call it, and we add microemulsion 1 to microemulsion 2 very quickly, that is, just immediately mix them together, we get the formation of these beautiful needles. When we use the same solvent, but the rate of addition is slower, so this is the course of a minute, this is a course of an hour or hours perhaps, we get these beautiful hexagonal nanoplates. So again, the only difference being the rate of addition in this case. And when we use any old rate of addition, whether it be fast or slow, if we change the solvent within the microemulsion, we get the formation of these long, as we affectionately call, noodles. And I just need to move my screen around a wee bit. There we go. And excitingly, what we've been able to determine using microED, using microED, so we were able to get an X-ray powder diffraction pattern, but the data was not really sufficient for us to be able to solve the crystal structure of this MOF. But from the microED data, we were able to solve the crystal structure of this MOF. And in fact, it's a MOF that has never previously been made before. And all of our attempts to prepare it using solvothermal syntheses has not been successful. So in other words, we think this is a MOF topology that is perhaps only accessible through the use of microemulsions. We believe that maybe this is perhaps a kinetic product rather than a thermodynamic product, but we're still investigating that there. The hexagons then, we have, again, a powder X-ray diffraction pattern. We're working on the electron diffraction, or obtaining the electron diffraction data. Again, it's probably a little bit hard to see on the screen there, but these hexagons tend to form stacks. And because of those stacks, we're getting multiple diffraction. And so it's been a little bit problematic getting a diffraction, electron diffraction data set that's suitable to solve the crystal structure. So that's still in progress. But from the powder X-ray diffraction pattern, we're starting to be a little bit more confident that it's, again, perhaps a new MOF, but that remains to be seen. And then with the noodles, this is a very well-known structure that can and has been produced on the macroscopic scale. So again, this gives us a little bit of direction now to start determining how and why the spheres, how they're directed into needles, hexagons versus noodles, once we have the final crystal structure for all three and all of the synthetic conditions. And hopefully now we can go back and look at, well, we can use this information then while rate of addition didn't seem to have an effect on ZIF8. If we were to have only studied this MOF here, rate of addition also would have seemed like it didn't have an effect on the resulting crystal structure or morphology or anything else. But in fact, with different solvent conditions, the rate of addition can have very, very important and very significant differences. So this gives us some information about which parameters we may want to adjust in combination with each other in order to hopefully learn some more about the mechanisms of growth of these nanocrystals. And perhaps along the way, develop or discover some new MOF topologies, which is exciting. Lastly, just very briefly, we've also been working on tuning the surface chemistries of these crystals. So this was a MOF that was formed from an adamantane-based ligand and 4 carboxylic acid groups combined with zinc metal. This is one that was reported by one of my colleagues, Professor Lyle Hanton here at the University of Otago. And by adjusting the, if we carry out the synthesis under conditions of excess ligand, so if we have our metal ion here and our microemulsion with metal is added to our microemulsion with ligand, and we control the rate of addition such that the crystals grow under conditions of excess metal ion in all cases, we can see that we can start to tune the crystal structures so that under conditions of the highest excess ligand, we get the most negative zeta potential. So these were in fact dispersible. So again, another advantage of making these MOFs on the nanoscale is that we can disperse them, and we can tune then the surface chemistry. So we can go from nanocrystals that are non-dispersible to those that are very dispersible and with a very negative zeta potential at high pH, indicating then that the surface of the nanocrystal are terminating at the ligand rather than terminating at the metal ion. So now we want to try and go in the other direction, and can we intentionally create the crystals so that they have a high density of metal ions at the surface? And you can imagine then what that allows us to do. So if the crystals terminate with if they predominantly terminate with the ligand, then we can use these carboxylic acid groups perhaps to start incorporating these nanocrystals into gels or other polymer type matrices to form hybrid materials. Alternatively, if they predominantly terminate at the metal ion, well, then we can start utilizing them more for catalysis, for example, where we have a very high surface area because they're nanoscale, but also have a high density of metal ions at that surface or the surface of the nanocrystal. So that's work that's ongoing. So I'll just finish up by saying, hopefully I've demonstrated today that microemulsion-based synthesis opens up some new possibilities for rational design and preparation of nanomorphs with controlled properties such as the variation in size, morphology, topology, and enhanced functionality. That there's a possibility using microemulsions for unique nanoscale MOFs with structures that have so far been unattainable in bulk form. And that this is an approach that is, as I said, this is really just the beginning of our story. So this is an approach that's hopefully rich for further development. That's meant to say strong potential to lead to new insight, which will really be of some great importance for the development of MOFs and MOF-based materials in the future. So I've just listed there, I'd like to acknowledge my current and past research group members who have worked on this MOF-based project, and my collaborators, and certainly the funding bodies. And thank you very much again to the conference organizers and for everybody who is listening. Cheers.
Thank you, Carla, for the nice talk on the microemulsions. To summarize what Dr. Carla presented now, she explained the difference between the nano and microemulsion and the challenges involved in the preparation and characterization of the microemulsions. There are a bunch of questions so from the audience side, and then I have 1 or 2 questions from my side. So here, can you really throw some light on your experience with the preparation on a ligand to metal addition or on a metal to ligand addition? So in terms of the size and then the properties.
Sorry, can you repeat the question?
Can you throw some light on your experience when you really prepare ligand to metal addition or metal to ligand addition in terms of their size and properties?
It depends on the system, and it depends very much on the solvent conditions that you're using when you add ligand to metal versus metal to ligand. It also very much depends on the rate of addition that you're adding one to the other, whether it's quickly or whether it's over a period of minutes or hours or days. Yeah, it very quickly becomes quite complicated. And most of the answer is it depends on. So this is what we're hoping to do over time, is to start to extract what depends on what. And now that we have some new information, we can go back and use that information for previous syntheses, and kind of one step at a time, extract more information and extract more information.
Okay. So there is one other query from the audience. Since we are using organic ligands in MOFs, so what is the range of temperature is favorable for synthesizing MOF? And what is the upper threshold limit of the temperature in this case?
I would say that depends on the continuous phase that you're using. So many of the cases we use heptane. So if the boiling point of heptane is 70 or 80 degrees, that's going to be your upper limit, perhaps. We've always had success at room temperature, even when the bulk synthesis or the conventional hydrothermal synthesis requires elevated temperatures. We've been able to make them at room temperature.
So the next query is how to tune the porosity of MOFs in the case of gas trapping applications. What are the methods that has been used?
What was the last part of the question, sorry?
What are the methods that has been used for preparation?
What other metals have been used?
Yes, methods.
Metals. We've used zinc and copper and gadolinium and iron and cobalt, and I think that's what we've looked at so far. I feel like
what are the different kinds of methodologies?
Sorry?
Methodologies.
Oh, methodologies. Sorry. For tuning.
Yes.
For tuning the pore size.
Yes, tuning the pore size.
We find that simply making them with the microemulsion method always leads to mesopores as well as the micropores. So if it's a known MOF, the micropores are as they are, plus there are mesopores as well. Other than that, tuning the micropores is simply tuning the topology. So for us, say for the last example was changing the rate of addition, changing the solvent conditions, we get a new MOF and therefore different porosity. So the same types of approaches you might use in bulk scale in terms of isoreticulation or other approaches for tuning pore size can certainly work on the nanoscale as well.
Okay. So how the size of a ligand can affect the activity of a complex?
Sorry?
How the size of a ligand can affect the activity of a complex?
Size of the ligand. Size of the ligand affect the activity in what sense?
Since the audience didn't really give too much information here, how the size of a ligand can affect the activity of a complex. There's a query they made.
I'm not sure. Sorry, I'm not sure how to. I'm not sure I understand the.
So, what's the role of temperature and the speed for the synthesis of nanoparticles? What's the role of temperature and the speed for the synthesis of nanoparticles?
Temperature. We haven't looked at adjusting the temperature. I certainly think that it would speed it up speed up the synthesis, but we haven't started. There's so many other things to play around with at the moment that we haven't really started adjusting the temperature. And what was the second one? Sorry.
Speed for the synthesis of the nanoparticles. Speed.
How does the
How
temperature?
much RPM you can really give for synthesis of the nanoparticles? RPM.
Ooh, RPM, good question. It's just under magnetic stirring. I haven't measured the RPM, sorry.
Yeah, so thank you, Kalra. So it was a really nice talk.
Thank you.
Over to Dr. Nirmala Grace for concluding the session.
Thanks very much.
Thank you, Dr. Prakasam, for sharing the session. And thank you once again, Dr. Karla, for a nice talk on metal organic frameworks. So a small announcement to the participants. We'll leave the session and join back with the same link to have the lecture with Dr. Madhu. Madhu, good morning. Yeah, Nirmala here. So would you mind leaving the session and joining back the same